Displacement, this function here, that's the displacement function. Okay, all well and good, gives us some units there. We've got centimetres per second, centimetres, and the time is seconds. Part A, find expressions for the velocity and acceleration and draw sine diagrams of both. Okay, well the velocity is going to be the derivative of s. Okay, so we differentiate this to get the velocity. That's going to be 6t squared, take 18t plus 12. Okay. The acceleration is going to be the derivative of the velocity. So if we differentiate the acceleration there, we're going to get 18t, take 18. All right. Now, if we want to jump straight to sine diagrams, okay, you could just draw them alongside here. All right, there's the velocity and there's the acceleration, and it is helpful to draw them right beneath each other when we're talking about kinematics. And the way we could do that is just by graphing these functions. Okay, graphing these functions and drawing the sine diagram straight away. Okay. Nonetheless, I'm going to go through a manual argument because that's what we've been doing each of the times. So with this function, if I want to find the roots, okay, firstly, I know that it's going to go positive, negative, positive because it has positive a value, all right, which means it's opening upwards. So it's coming from above, below, and then above the x-axis. But first, let's factorise it. So let's consider v of t, which is 6t squared take 18t plus 12. We can factorise 6 out the front, and we've got t squared take 3t plus 2, which we could write as t take 1 times t take 2. Okay, which means the values of t that make it equal to 0 are 1 or 2.
Where'd the n come from? Yeah, so I was wondering too.
That's a 12. Tidy that one up a bit. Yeah. So PR is 6 and our number is 6050. Okay, so let's get that from the graph together. Okay, so let's say you've opened up your calculator. I just do it on Desmos because it's a bit easier to use on the computer. It's not as fiddly, not as clunky. So this is the function that I want to know the sine diagram of. I'm just going to go 6x squared, take 18x plus 12. Okay, and look at that. You can see the roots are 1 and 2. You can g-solve the roots, okay, 1 and 2, and you can see it's above the x-axis, below, and then above. So we've generated the sine diagram. Okay, and then we move on to this. All right, if I want to find when that equals 0, that's 18t take 18. I mean, maybe you can see the solution. All right, we've also got t is 1. And I could see that again from here as well if I were to graph that function, 18x take 18, okay, it crosses at 1, and it goes from below the x-axis to above. And we know that because it's the equation of a line, it has positive slope. The coefficient of the variable is positive, which means it's going like that, okay, across the axis. Excellent. So, look, I've demonstrated some manual process. You can go bam, mean, get those marks.
Is there a,
Yeah.
it should be 12t.
Thank you. Where are we going there? There, that's 12, and so that's going to change that. 12t take 18. Okay, so let's figure this one out. That's going to be 18 on 12, which is 3 on 2. All right, so yeah, I've graphed the wrong function there. Thank you, thank you, thank you, thank you. All right, and you can see that there, that's 2/3, isn't it? 1.5, yeah, sorry. 3 halves. 3 on 2 is 1.5. Okay, so look, where are you getting marks for part A? Stating the velocity, drawing a sine diagram, stating the acceleration, drawing a sine diagram. Okay, this process here, that's just sort of descriptive, and that's consolidation of things that we've talked about before. Okay, let's look at the next part of the question. find the initial conditions. Okay, so that means when time is 0, what's the displacement, what's the velocity, what's the acceleration? So to answer part B, S of 0. If you take the number 0 and you put it into here, you're going to get -5. Okay, what is V of 0? You take the number 0, okay, we put it into the velocity function, and we've got 12. And then that should be, that's the 12 there. And then you take the 0 and you put it into the acceleration function, and you've got -18. Okay, so unit for velocity, unit for acceleration. Now, what is the significance of this? Okay, if we think about the particle that's moving, okay, when time is 0, so initially it is 5 centimeters left of origin, okay, 5 centimeters left because it's negative, all right, just by convention, okay, if that 0 to the right is positive and to the left is negative, so we're initially starting 5 centimeters left of origin, but we have positive velocity, okay, the velocity is a positive number, which means it's moving to the right, okay, we have positive velocity moving right. If we have negative velocity, it means it's moving to the left, okay, and it's got negative acceleration. So what that means for us is it's moving in this direction, but it's slowing down as it's moving in that direction. They're the initial conditions of the particle. Okay, so 3 marks just for doing all that. V of 0, A of 0, and the displacement of 0. Determine when its speed is increasing. Okay, so this is a question that we've sort of focused on a bit. Now we have speed is increasing. I need to fix that up, don't I? Speed is increasing when the sine diagram of V of t and A of t have the same sign. Okay, so that is they're both negative or they're both positive. Okay, so speed increasing. Let's look at the sine diagram here. We can see they're both positive, all right, quite easily there. We can see they're both positive for values of time greater than 2. So that's a pretty easy one to answer. Values of time that are larger than 2. And we can see they're both negative. Okay, so the acceleration is negative up until 2/3. The velocity is negative between 1 and 2. They're going to be the same between 1 and 2/3. They're both negative over that interval. Okay, so like if you think, you can draw a line down here. Okay, the acceleration is negative up till there, and the velocity is negative up till there as well, between 1 and 2/3. Okay, so 1, 2, sorry, I shouldn't say 2/3, I should say 3/2. 3/2 is what it is. 2/3. Okay, does that make sense? As long as they have the same sign. Okay, so you're just going to look for where are they both positive, where are they both negative. Okay, so that's part C. If you want to practice that, let me know. Part D. Find the times and positions when it changes direction. All right, I'm going to get rid of this dotted line there. Okay, well, it changes direction when the velocity changes from positive to negative or negative to positive. Okay, so what this tells us here is initially we have positive velocity and then we have negative velocity. All right, so what that means is it's moving to the right and then it starts moving to the left. Okay, and then it's moving to the left and then it stops and starts moving to the right again. So it's sort of going to the right, to the left, and then back to the right. Okay? So these are the points when it's changing direction. So this is to answer part D. It changes direction at t is 1 and t is 2. Okay, so they're the times when it changes direction. It wants the position. What is the position when it changes direction? Okay? So what that means is what's the displacement? What's the displacement when time is 1? What's the displacement when time is 2? And this is where it is helpful to have graphed the function, so you can just g-solve those values. So the function, the initial function we've got is 2x to the power of 3. Take 9x squared plus 12x. Take 5. There you go. I'm going to turn the others off. And so I'm interested in the displacement when time is 1 and time is 2. When time is 1, the displacement is 0. time is 2, the displacement is 1, minus 1. Very good. Okay, so it changes direction when time is 1 at 0 centimeters, and when time is 2 seconds at minus 1 centimeter. Okay, so that's that part there. Draw a diagram to illustrate the motion over the first 3 seconds. Okay, so in order to do that, to draw the motion diagram, we've got S of 1 and S of 2. We need the displacement when time is 3. We've even got S of 0 over here, so we've sort of got all those points in time. So to find S of 3, I'm just going to go back to my graph. When time is 3, so what's that here? The displacement is 4, positive 4 meters. Okay, time is 3, the displacement is centimeters. It's 4 centimeters. Okay, we're ready for that motion diagram. So here it is. Now remember, a motion diagram is an indication of its displacement on an axis. So we have the point of origin is 0, and we have that the particle starts at minus 5 centimeters and is initially moving to the right, isn't it? Okay, when it starts, it has positive velocity, which means it's moving to the right. Okay, we have, it changes direction when time is 1 at 0 centimeters. So it changes direction here, and then it changes direction again at minus 1 centimeter here. Okay, so we're starting here, we're moving to the right, changes direction, moves to the left, changes direction. Okay, and then we have S of 3 is over here at 4 centimeters. That's what we found here. When time is 3, the displacement is 4 centimeters. Okay, so let's label these points. Here's the displacement when time is 0. Here's displacement when time is 1. Here's the displacement when time is 2. And here's the displacement when time is 3. And let's put a unit there to show that's 1 centimeter. It's not a very good scale here, but you get the idea. Okay, so that's the motion diagram. And then determine how far it's traveled over those first 3 seconds. So it started here, it's moving to the right, it stops, moves back to the left, it stops, and then moves to the right. And to find the total distance, we need the sum of each of those segments. Okay? So over the first segment, it's moved 5 centimeters. Okay, from there to there, 5 centimeters. Over the second segment, it's moved 1 centimeter. Distance from there to there is 1 centimeter, so we have 5 plus 1 plus. And then it's moved from minus 1 to positive 4. That should be minus 1. From minus 1 to positive 4 plus another 5. And so the total distance it's travelled is 11 centimetres. Okay, so that's what the trend the kinematics problems are going to follow. Okay, so let's break it down. What do they ask for? Find velocity, acceleration, draw their sine diagrams. Okay, go straight to your calculator, done. What's the initial conditions when time is 0? What's the velocity? What's the acceleration? What's the displacement? Okay, easy marks here, I'm thinking. Okay, speed increasing, that's where it gets a little bit tricky. Okay, that's where we have to look at the sine diagram and go, when are they both negative and when are they both positive? Okay, and then answer with intervals. When does it change direction? That's relatively easy. That's just looking at the velocity sine diagram and going, when does it change from positive to negative? Okay, it changes at that point in time and that point in time. And then what's the position? Well, we take those time values, put them into the original function. Okay, and then to draw a motion diagram, we just list the first sort of points of motion that we're interested in. Okay, and then we just plot it accordingly. Okay, here it's going this way, and then the total distance, the sum of each segment. So it's going to follow that trend. They're the sort of key concepts we're interested in. Okay, I do want to show you a really cool trick. So if you could pull your calculator out. So this is sort of some new cool calculator hacks for you guys. So I'll just make it a bit bigger here. View, count screen. Okay, let's go down into graph. And let's just say we have this original function here. Let's put all that information in there. 2x to the power of 3. And then we have plus, take 9x squared. plus 12x, take 5. Okay, so that's not revolutionary, what we've shown you there, putting that in the calculator. But watch this. Go down to y2, okay, so you've typed it in, and then we're hovering over y2 there. We're going to press Option, Calc, d on dx. Calculate the derivative for me of y1. And then you just press enter. And now it is going to graph for you the derivative function. Okay, so I can unselect the first one. Let's say you didn't even know how to find the derivative. You can still get your calculator to draw the graph of the velocity function. Okay, even if you don't know how to find it. Okay, and you can see there it's got the same roots, 1 and 2. It's going positive, negative, positive. Okay, so you can do it there. And you can even go, you know, to do it again. Option, Calc. Well, now I want the derivative of y2. Okay, I want the derivative of the derivative. I want the acceleration function. Okay, no, you can't do that. You have to do it like this. Option, Calc, d squared. Okay, so d squared means second derivative of the first function, which is y1. Okay, so that will be how you generate the acceleration function. Right, that's that one there that we talked about. There's its root 3 on 2. Okay, so that's a pretty cool trick you can use. Right, let's do some more. Okay.